Okay, a car has a mass of 710 kgs. It starts from rest and travels 20 meters in 3 seconds. I'll draw a little diagram. Starts at rest, and then it's going pretty fast a bit later. Here's my positive. Make a quantitative force diagram. So that's, again, numbers. So it's accelerating. So I don't know why I'm drawing the whole thing, but maybe I'll draw it again over here. Those will be the same. It's uniformly accelerating. So I know this is 17 times 9.8, 6958. And this is 6958 newtons. The thing that causes the acceleration will be traction on the wheels by the road, but I don't know what that is. So in terms of quantitative, I don't know what that value is. Calculate the acceleration using an acceleration tool, either a formula or a graph. At this point, I like using formulas because they're faster. I could still do it with a graph if I wanted to. I'd definitely do this one. Yeah, maybe not a graph. Maybe this one's definitely a formula. Right, what have I got? I always write down what I've got first. So I know my initial velocity was 0. I know my time is 3 seconds. I know my distance is 20 meters. I want to find my acceleration. And if I go back a couple of pages to what I've got, I don't have final velocity. So I'm not going to use this one. I'm not going to use this one. I'm going to use this middle one because I've got distance, I've got initial velocity, time, half at squared. My initial velocity is 0, so I'm not even going to write that in. 0 times t is 0, so I'm just going to write b equals half at squared. Equals half at squared. And just backtrack a bit, initial velocity is 0. It says it there. That's where I got that from. I want to find a, so I could put the numbers in and then rearrange it, or I could rearrange it first. Last time I put the numbers in, this time I'm going to do it the other way. So to get rid of a half, I'm going to times by 2. Now I've got 2d equals at squared. To get rid of the t squared, I'm going to divide by t squared. So now I have 2d over t squared equals a. That is 2 times 20 over 3 squared, which is 40 over 9. I can't do that in my head quickly. Something like 5, isn't it? 4.5 or something. 4.4 meters per second squared. Calculate the net force on the car. So this question is like the other question from question 1, but backwards. This one I had the force diagram first. I did total force MA, and then I went through and used an equation of motion. This time I'm using the equation of motion first, work out my A. Now I'm going back to this, which is 17 times 4.4. So times 17 equals, and by the way, in my calculator, I didn't put 4.4. I used the answer button because this had more decimal places, and I wanted to keep them going through the calculations right till the end. So I did, in my calculator, I did 17 times answer, and that gave me 315, 5.5 recurring, and that is newtons. And if I put that into two significant figures, because that's what this is, this is 3 significant figures, and this is 2 significant figures. So I've done 2 significant figures. Round this 5 up, so it becomes 3,200 newtons. Right, last one. A 65 kg person dives into the water from a 10-meter platform. I think you can assume that they start from rest. I like to draw a diagram even before I draw my force diagram. So then they end up going down here, and then by the time they're almost at the water, they're going really fast. Draw a force diagram for this person. So let's draw them as they're speeding up. What forces are on them? Force of gravity on person by Earth. And from a 10-meter platform, I don't even think the air resistance is really going to come into it. So I'm just going to leave that off. And that's it. I can work out it. I know what her force of gravity is because she's 65 kgs. So that equals 65 kgs times 9.8 newtons for every kg, which equals 65 times 9.8, 637 newtons. Okay, what's her final speed just before she enters the water? Oh, that's tough. And this is a tough question, but we've always been linking things with the acceleration. This one here, we worked out the acceleration and we used it to link it. Question 1, we worked out the acceleration and we used it to link between forces and speeds. So I'm going to do this first. So acceleration is total force over mass, and that equals 637 over her mass of 65. And if I do that on the calculator, lo and behold, I get 9.8 meters per second squared. And that's a good point. The gravitational field strength is equal to 9.8 newtons per kg. But also, if there's no other forces acting on something, their acceleration due to gravity is equal to 9.8 meters per second squared. Now it gets to the point where you can just skip this whole step I've done, if you remember it and you know it. And people often skip the step by accident and they just use this number without realizing where it came from. But that's what you do. If there's only one force and you go through this process, you're going to end up back with 9.8 meters per second squared, starting from gravity is 9.8 newtons for every kg. But we want final speed. So we've got an initial speed of 0 meters a second. We've got distance is 10 meters. We want to find final speed, and we've got acceleration is 9.8 meters per second squared. They're falling down this way. Let's say that's their starting point, and this is the positive direction. So that's the same direction as this. So acceleration in this case is positive. A formula that has those ones in it, if you look back on page 8, top of page 8, the one that has those in it is this one here. Vf squared equals Vi squared plus 2AD. Vi is 0, so Vf squared equals 2AD, which equals 2 times 9.8 times 10. Do that in my calculator. Now here's a bit of a trick. This is Vf squared. So to find Vf, we need to square root 196. And that equals, square root answer equals, hey, 14 meters per second. And that's the answer down there. Cool.